This meeting is being recorded.
Okay, so this week we're looking at the fifth section. We're looking at volume rendering based on 3D voxel grids. And so I guess let's just real quick look at what we're looking at here. Like before we were looking at noise patterns and stuff like that in the volume to give it some variation in the density. But we were using like Perlin noise, that kind of thing. And so that's, you can do a lot with that, but maybe you want to do, they give the example of simulating some smoke here. So looking at a situation where you do a simulation on a voxel grid and part of the state of that simulation is going to be this density field that we can use the same way that we were using the noise. And so we looked at in the previous chapter, you can create density fields using two different techniques. There's procedural or through some sort of simulation. So in this chapter, we're looking at the simulation aspect. We're not touching on how fluid sim works because that's a topic unto itself. And we're looking at the just the data that would be produced. So first thing, using a grid to store the density values. There are many different techniques for that, but they get a density field as an output. So for simplicity, we're going to assume that we have just this low resolution constant on all sides, and that the resolution is power 2, just for the sake of this lesson. In practice, that doesn't have to be the case. Also, we won't be transforming the grid in this lesson. That might be using a noise field to offset where you're reading or something like that. We treat it like an axis-aligned box, and we treat the the grid is subdividing that axis-aligned box. Yeah, okay. So they show just a real simple example of 8 by 8 by 8 and kind of what that would look like if you were to look at one slice of it. And they're looking at increasing density towards the center. So grids are nice to simulate the motion of fluids because the grid's voxels are set with some initial density, and this density is distributed among neighboring cells as time progresses. These voxels are the small volume elements we're looking at here. These little squares here, they represent a voxel, like kind of a flattened version of the voxel there. And yeah, so maybe this is the initial state before anything happens. So again, not really getting into the fluid sim, but the Navier-Stokes equation is one way that you would be doing the simulation and then getting the output to Raymarch here. Each voxel in the grid stores one unique density value. So that's a single channel. We're just looking at the opacity there. So 3D grids, it's an interesting analogy. I think they might have reversed part of that.
Yeah, I don't understand why fluid sim is the equivalent of image.
Yeah, I think that might be backwards. I think fluid sims are to 3D grids what bitmaps are to images. Yeah. If you were to, it's just some example contents. Yeah. would are the bitmap or the fluid sim, and then the 3D grid or the image is the container, I guess.
Like they're basically just saying that the fluid sim is being quantized down into like a finite set of samples.
Yeah, that's the voxels there. Yeah.
Okay. Yeah.
3D grid storing density values is simple to define in any programming language, though there are subtleties that we'll look into at the end of this chapter. Besides the resolution, we also need to define the size of the grid in world space. So that's the size of the object in the scene. You can do this in different ways, but for convenience, excuse me, we're doing this by setting a minimum and maximum bound for the grid in world space. So they just pick out some values here, -2, -2, 2, and 2, 2, 2. So it's
Oh, sorry, JB. Can you check the waiting room on the?
Sorry. Yeah. Okay. Yeah, good.
There we go. Thanks.
Cool. Yeah. Sorry, I didn't see you there. Cool. So we went ahead and started. We're just getting through the first little bit here. They were showing off a kind of, you might want to represent something like this, output of a simulation. So basically, we're talking about voxels this chapter, keeping our data on a 3D grid.
Cool.
So so we need to figure out what the resolution of the voxel data is, and then we can also define the size of the grid in world space. So that's what they've defined there is flat, because it has no extents along the Z, but it's neither here nor there. Anyway, think about it from 0 to 1 on each axis. That's as easy as it gets. So because our grid is a cube, the values don't need to be symmetrical with respect to the world's origin. I don't know what that's trying to say, but the size of the grid in world space has to be the same on all 3 dimensions if we want those voxels to be cubes. Otherwise, you're going to start to get, what is it, anisotropic or isotropic behavior, I guess. Yeah, it's going to be different when you look at it from different directions, because your voxels are differently shaped or different length on some axis or something like that. Defining our grid in world space that way is convenient, as the minimum and maximum extents can be plugged directly into the Raybox intersection routine. And then we can subdivide those axes in order to reference the 3-dimensional texture data, or whatever, however we're holding the grid data. So we already know how to compute values for T0 and T1 for any ray that intersects a cube. We get the near and far intersection points with the cube. And then we can take some number of steps in between those 2 points. So looking at code from previous chapters, looking at doing cubes now instead of spheres. So they have a grid here, pointer to the data, dimension. I assume that's the number of voxels along one axis. And then we have the bounding box defined as minimums and maximums for X, Y, and Z. So we have the ray box intersection routine, and we're going to basically be getting back out this T0 and T1. And those 2 values are going to be, like I say, the near and far intersection points. So when we do integrate through, we're going to be
Hey, JB, can you check the waiting room?
oh yeah, sorry. Yeah, it's just me this week, so cool. So yeah, so we got we'll get our T0 and T1 locally, and then we take and see if we hit the box. If that returns true, then we're going to have values in T0 and T1, and we can ray march from T0 to T1. And that's going to be a very similar process to what we did last week and the week before. So then they're looking at doing some more interesting rendering here by having a camera to world matrix that's going to transform, I assume, the origin and direction of the ray for our camera. Okay, so and they just have a little bit of stuff about allocating and freeing the memory associated with that that opacity grid. Okay, so not worrying too much about that part of it now. We're looking at that later. For right now, we just want to create a contiguous memory block and store as many float values as there are voxels in the grid. We move the values from disk to memory. Nothing fancy. So looking at a constant value, it's very similar to what we've done before. It's all homogeneous because it's all the same data for all those different voxels. So now that we know we're going to be using a 3D grid to store the density field values, this grid has a resolution and size. We know how to calculate the points where the ray intersects the box. And let's see how we read the grid density values. Okay. So a couple different approaches here. I haven't looked at this. I think this is... Okay, that's more complicated stuff. I might look at that later. So we have to find every single cell where in the grid where the ray intersects to see if the geometry that each of the intersected cells contains does intersect with the ray as well. Okay, so I guess they're talking about like each voxel would kind of have like a list of geometry that's inside of it, kind of thing, if you were going to have a mesh here. Not super complicated, not super trivial, especially if you want to make it fast and accurate. So you might worry that we have to go through this process again. Ray marching is a trivial test since all we care about are the sample points along the ray. Okay. Yeah, so this is if we're looking at the exact same ray marching stuff that we've been doing before, where we take a constant step size, or even if we take a constant step size along the ray, we're going to get this kind of aliasing here where we come through and we step here, okay, that's in that voxel. We step here, that's in that voxel, and then we kind of step over this because we took a big enough step that we're over in this voxel. So that's called aliasing, and that's just kind of a consequence of your you've got to pick your step size appropriately, basically. There are algorithms to get you exact intersections, like what they're calling ray tracing here. There's just things like DDA is one, digital differential analysis. And then there's another one I've heard of called Supercover that does something very similar. And so that's basically, we're just going to be getting those intersection points, and then we can do steps that are these lengths between the intersection points. So as we know the positions of those points, all we have to do is figure out the position of the voxel in the grid, read the density value, and okay. See how we go from the sample point to the voxel's coordinates and read the value from memory using those coordinates. So reading the density values as we march along, we need to change, all we need to change in the code we use so far is the eval density function. Instead of evaluating the density field, as noise, we'll read from memory with our explicit data instead. So it's a relatively small change. Everything else works the same. And we know that the sample point is always contained within the bounds of the grid because it should be between the intersection points with the box. Okay. So it basically needs to know the bounds that you set there as well. Different names, call it a lookup or pro. Basically, what we've got to do is remap our range for each axis from the minimum to the maximum to whatever the dimension is on the texture. So if you think about normalizing it, it's, you get it in the range 0 to 1, then you can just multiply that by the resolution, and then you get your texture location. And if you want to get fractional stuff there, you can also use that to do interpolation between neighboring cells and get that's another thing you could do there. Otherwise, you would just know that you're in 3, 3 in this particular sample point, and you just go 0, 1, 2, 3, and then however you're keeping your grid in memory, you've just got to index into it and be able to read it out. So what we need to do is find a correspondence between the sample point and the voxel in the grid that it falls into. So we need to convert that sample point into discrete grid coordinates. To do so, we need to transform the point from world space into object space. All this to say that basically it's just what we saw in the image. It's just we are remapping the extents to the space in which our grid is defined. Okay. So if we look at the 2D example above, we can see that the point coordinates 3.36 and 3.28 in voxels is what we get for that point in voxel space. From there, we know that finding the index of the voxel in memory is just a matter of multiplying the integer part of the y coordinate by 8 plus 3. So that's, just indexing into that array. So just representing the 2D grid as a flat array. So they take their indices, they cast the position, they solve for a voxel location, take and cast it as an integer, the floor of that, and then we can take and right, so z times the resolution times the resolution, and y times the resolution once, because that's just kind of the way that all kind of shakes out when you're flattening that array. So again, like for the Perlin noise function, which has a similar need for converting points from world space to lattice space, we use the floor function because if the normalized point coordinates are lower than 0, we want the function to return 0 and not -1, which a simple static cast would eventually do. I'm not sure that makes sense. Call this method nearest neighbor search because we're directly reading from the voxel that it falls into. We're not doing any sort of interpolation. Because all you do is retrieve the coordinates and sample the memory one time, and you don't do any interpolation. yeah, so you might be doing like linear interpolation or something higher order, more complex. So if we have a density field for this smoke plume, this might be something that we're able to render just with the code from last week, because we changed out the eval density function from noise to now sampling the grid. And that's, again, remapping that 0 to 1 or whatever your bounds are to the voxel coordinates. So as you know, we aim to provide examples that have no dependency on our external libraries. So we're not using anything like OpenBDB or those types of hierarchical things that get much more complicated to parse and store and get into your program here. So it's really just, just creating a flat array with some data here, and it's about as simple format to read and write as you could possibly have for that kind of thing. So OpenVDB works on similar principles, but they support compression and multi-resolution and sparse volumes. So those are things that you can do to make the memory footprint smaller, make traversal faster, those types of things. Because sparse volumes in particular, it's you could have some elements are much larger than others, and they might represent empty space, the kind of negative space in between voxels there. Okay, so let's see. Magenta voxel in the figure below is our 0, 0, 0, and then our maximum is 888 or 777, I guess. Anyway, if we map the voxels in a simple float array like we do when we dump the data out to a file, first voxel in this array is index 0, and the last one has index 511, zero-based array. Yep. And so to compute the index from a voxel, we just do that same thing we saw before, indexing into the flat array there. So it's the most basic way of getting a result, but we can improve the image quality using what we call trilinear. So trilinear interpolation. Basic idea is voxel represents a single density value, but a sample point doesn't necessarily have to be, it can be anywhere within the volume of that voxel. So it makes sense to assume that the density value at this location should somehow mix between the density of the surrounding voxels. They give the example here where we're looking at 8 voxels. And yeah, we can use the fractional position within that voxel that the sample point is in to mix between them. So by calculating the distance from the sample point to each of these 8 voxels and using the distances to weigh the contribution of each one, we can get the final result. So this is linear interpolation, but on 3 axes. So equation we're using to interpolate 2 values is a times 1 minus weight plus b times weight, where the weight varies from 0 to 1. And that's the fractional position on the axis. So if you were at whatever they said, 3.36, that 0.36 is going to be your weight. And A and B there represent essentially the voxel values at 3 and 4. Because you're basically you're going to want to see what's on either side of that. In 2D, it's called bilinear. It requires 4, and in 3, it's trilinear and requires 8. And this is just because you need the data. You need to interpolate on each axis. So in 3D, it looks like this. Note that the equation used to interpolate is called an interpolant, and in this case, it's a first-order polynomial. We assume that the density is stored in a given voxel as the value at the sample point, or that the sample point should take if it was exactly in the middle of that voxel. Due to the nature of trilinear interpolation, to get that result, we just need to shift the sample position in voxel space by -0.5. Or you could assume that it's at 0 and then it's just offset by a little bit. And so they're doing it as a triply nested loop here, and they are figuring out the weights. Code seems a little bit like nonsense, but
Yeah, they're like, are they doing pointer arithmetic and all those absolute calls?
I'm not sure.
I think they're like subtracting the index from the pointer to index it that way. Maybe.
It looks
Well, but
like
they only read from the grid once, I think, isn't it? Or
Yeah, I think
yeah,
they're
it's like just in grid math.
yeah. So X is a pointer, right? Is that true or not? Yeah. All right. P lattice dot
well,
X.
in any
Oh.
event, you'd be. Well, okay, wait.
Oh
Yeah,
wait,
so yeah,
P,
the
P
only
lattice is a vector. I'm so used to the lowercase p meaning pointer.
Oh. But yeah, the grid function that they call in the innermost for loop, that probably
Yeah. Okay.
that's
Shit,
probably dereferencing a pointer.
I didn't even pay attention to the fact it was instead of loop. Yeah, okay. Great. So yeah, point being, we're looking at rounded down and rounded up, and then interpolating between the two. So nearest neighbor, we get these discrete values for each cell. Linear interpolation, we're looking at something where we have a little bit smoother variation. We don't have the sharp delineations between voxels anymore. And there's higher order stuff that you could do too. And here they explain it visually with dx0 and dx1, dy0 and dy1 to show how these things are weighted. So let's see. Okay, if you're just gonna, yeah, you basically you're averaging here because it's, I guess they're summing it. Okay, in any event, we're getting the interpolated result. We need to offset our sample point by half a voxel in voxel space. If we keep the example of our sample point that falls exactly right in the middle of the 4 voxels, sample point with the offset applied is now located right in the middle of the lower left voxel. What we do next, compute these distances from this point to each one of the voxel boundaries. In our 2D case illustration, this is represented by dx0. That's the interpolant along the x-axis, dy0. It's the interpolant on the y-axis. And we're using those to blend together. Okay. Not to beat that to death or anything. That's right. We're just interpolating. Um, okay. So um, okay. Yeah, this kind of gives you an example of what that would look like as output. So nearest neighbor, you're going to see grid artifacts. Trilinear, you're going to start to see that disappear. But at certain scales or certain situations, you might see those come back. To some extent, you might have to figure out a better interpolation scheme. So you can see that it's softer. The improvement comes at a price because now we have 4 samples to take. We need to read 4 values out of that data array instead of just the 1.
Don't you need to
and
take 8 samples for trilinear?
Oh, I'm sorry. Yeah, that's right. 8. Yeah,
Yeah,
8.
bilinear, you take 4.
Right. That's and then additionally, you got to do the math to mix those values. So looking at OpenVDB and how that might be used. I guess this is kind of implementation specific. I've never actually looked at OpenVDB and how that works. I went to a talk on it once, and my understanding that it's basically it's a hierarchical kind of thing where you have like a parent grid, and then there's subgrids that might be subdivided more or less based on what the data is that it's holding. And so I guess this is just kind of showing what the code looks like for that and how you would do your interpolation with that that type of data. So sample function is for fetching the values in the stored in the 8 voxels and probe values, and then the voxels are interpolated as described above. Function interpolate is nothing other than a linear interpolation, or often called LERP or mix. So volume caches. Guess we're not going to talk about. Let's see. Interpolation scheme, yeah, cubic and filter kernels. And you start to look at higher order filters, and they're saying 64 voxels starts to get much more expensive. Storing more data alongside density. This might be things like material properties that might be, they're giving the example of temperature, velocity. Those might be data parameters that you can visualize in the volume. It might be color. It might be like a emissive something or other. And you can start to model some more complex effects there. If you render volume caches for production purposes, you should probably care about filtering and levels of detail. Problem is, when you're rendering volume caches, the same as with rendering textures. Textures have a fixed resolution. If you render an object to which a given texture is applied from super far away, you assume your object is just a few pixels wide in the image. As the object moves or the camera moves, you're going to get aliasing from that. Just it has to do with how that's being sampled. That's the relative spatial frequency there. The texture is much higher frequency than what it's being sampled at. So this is kind of what where the necessity for mipmaps comes in. These are pre-computed levels of detail that are essentially already averaging the contents across the larger area. And those can be sampled based on the delta between pixels, and we can kind of basically we know what level to look at in order to get a good sampling from a higher MIP level. If you're familiar with the concept of MIPMAP, it makes a lot of sense. That's what they're used for. And they have another something or other they're calling brick maps, looking like Minecraft objects, used by Pixar's RenderMan team. Generally, the idea is having a cache storing multiple resolutions of its data and not particularly new or uncommon. So just multiple levels of subdivision so that we don't have to necessarily reference the native resolution data every time and have those types of aliasing issues. Because if this is only covering a half dozen pixels across the screen here, it doesn't really make sense to be looking at this version because we're going to have those aliasing issues. Building brick maps, very similar to building the textures map levels. We're taking the average of 8 voxels instead of 4 for a flat texture. Dealing with grids whose resolution of power of 2 is convenient because we know otherwise you would have to pad it or something like that in order to get the MIP chain to go all the way down to 1. So looking at how you create these levels from our original fluid sim caches, this is just a grid that's 128 on a side, and you could do this recursively, or you could do this a number of different ways. Point being, it's just it's a pre-computed averaging in each higher level of detail, each higher MIP level. And so explaining, kind of illustrating what that would look like, we're looking at a level 0 here at a resolution of 128, then down to 64, 32, 16, you're starting to see the cube shapes, and then 8. It's a very low fidelity representation of the data. So motion blur, what about 3D motion blur? To render this, we need to store the voxel with the motion of the fluid. Okay, you can make things as complicated as you want with that. Advection, I thought we weren't talking about simulation, but I guess we are. And sparse volumes are something where some fraction of the grid is, it's a hierarchical structure. So you're looking at a situation where if a large group of voxels share the same data, we can just replace that with one larger sort of element. For example, this whole region here is constant black. We can just go ahead and set that to one big black pixel, or volume element, as the case may be. And that's like an octree type of setup. Okay, so that's, you divide the whole volume into 4, or in this case, in the flat image, it's into 4, and the volume it's into 8, and then recursively subdivide down to where you have data. And there's kind of what that would look like if you were rendering all the bounding boxes of all the leaf nodes. Okay, so sparse volumes are also useful in rendering. Large voxels are empty, can be skipped. Large voxels with uniform density can be rendered as homogeneous volumes. Okay, and that's another simplification. If we're looking at all these voxels are this gray value, then we can replace that with a gray value. And if we're doing those that what they called ray tracing earlier, and getting those intersection points at exact boundaries here, we know the distance between those two boundaries, and we can treat our step size that big, or however we want to try and do that. Topic of sparse volumes is important and large enough to deserve a lesson of its own. That gets complicated. If you're interested, you can also look up the Gigavoxels project. Let's see. Out of core rendering. Reason why we mentioned out of core rendering is right after sparse volumes. There is a reason why. Sparse volumes and octrees of bricks often have been designed to make it possible to render very large volume caches that wouldn't normally be renderable as a grid due to memory limitations. When you can't load the entire file into memory, you don't want to be limited in how large your simulation might be. What you do is only load from the cache using some kind of buffer mechanism. The bricks you need, the ones that are visible to the camera. This is, of course, only possible if your volume cache is organized as a collection of bricks that can be loaded on the fly. This topic will be covered in a future lesson. So you have to be mindful how you iterate through the grid data, and this is this has to do with how that array is flattened. If you iterate certain ways, you're going to be going through contiguous memory, and if you go not the best way, then you might be making big jumps, and that's bad for caches. Right. This is because of the way the data is laid out in memory. Yeah, and because it's all been flattened down into a flat array there. Okay. When we iterate out of order, it's likely to generate a lot of cache misses, and that decreases performance. Okay. You can bake lighting into the grid's voxels and read this data from the voxels at render time to skip the evaluation of the LI term, that's the incoming light term. This is what Veraldo does. Does both things in a computer. So there's a step that does the lighting and bakes the lighting into a 3D texture format, and so that's known. We take 2 texture reads during the ray march, and incoming light is known. The albedo and opacity of the volume is known at that point from those 2 texture reads. So you start baking again whenever the lighting or simulation changes, mostly mentioning it for reference and historical reasons. But you can do it in a computator if you have enough memory bandwidth. Deep shadow maps are about to become an artifact of the past, mentioning for the sake of completeness. The idea is to compute a shadow map per light in the scene, but rather than storing the depth value to the nearest object of the scene, deep shadow map stored the density of the volume instead as a function of distance. In other words, each pixel in the deep shadow map stores a curve that represents how the transmission through the volume changes as we move through it. So that's kind of along the lines of what Beer's law does. We're kind of pre-computing that into a map so that we can reference it when we're rendering. And then looking at the source code, looks like they have cached bin files for representing their simulation. Cool.
So I ran this code last week, and I missed that part at the very end because I didn't read it yet. where it says the cache, you have to unzip the cache file. Doing that right now. But last week it didn't work. I was curious if you guys are down to debug it, but I'm just running that, running this with the cache file again right now. See if it's working. Still not working. I don't know. Are you guys down to debug it? Or,
If you want to share your screen, yeah, go ahead.
okay. Okay. So this is what I'm running. This is what it says to run here. Look, I got Clang plus plus. This is the code. How do you? move this? Yeah, so this is chapter 5. This is the one that we just looked at.
Hmm.
Renders like 90 frames. So last time I ran it, I stored them here. There's these, so smoke, it's supposed to have something, but it's all nothing. So there's nothing in it. 90 frames of nothing.
Hmm.
This, all this spin stuff is what's in the cache file. So that's that. And I just unzipped it just now. Maybe I need to compile it again, or I don't know. It doesn't seem like it because it compiled successfully. So if I run this and compile it, and it's fine. It comes out with a render, which needs to be an exe on Windows. So I just, that's this here. Delete that one and rename the just compiled exe to render.exe, and then I run that and it starts rendering. So go 90. Last week it took about 2 hours to render all 90 frames, but I mean, does that one?
What if, just out of curiosity, what if inside of the maybe when you're loading the data, if you have it spit out all the values, just to see if we're getting all zeros or if there's actually data in those files.
Or just set a breakpoint at the place where it loads it and then dump out.
Yeah.
Look at
Yeah,
it in the
that-
watch window.
That's a better suggestion.
Yeah.
Well, I don't have the IDE here with Clang because it's in, you know, I just have the command line. So maybe I could do
Yeah,
like,
no, you can do it from, you're in, which program are you in? Is that,
this
what
is
editor?
Sublime Edit.
Oh, yeah, you probably have to do it from VS Code or something.
I can do
Or-
that. Let's go.
You could do that, or you could just do printfs.
The dump, but yeah, but it's
Yeah.
a really big file, right? So it may be hard to find.
Or use WinDBG.
Yeah. Is that command line still?
There's a new one that's like has a nice GUI and everything.
Ooh, another thing. Do you have a hex editor? You could look at the
It's somewhere. Yeah, somewhere I do. Let me see. Like here.
I think there's just HD on, or something like that on
This-
Windows.
okay.
If you're
Yeah,
on command line.
okay. So what should we do?
Uh,
a couple different approaches. Yeah.
You can just go to the directory, just open the directory in VS Code, I think.
Okay.
Where the render.exe is.
Yeah.
And I don't use VS Code very much though.
Yeah, I started recently because they deprecated Atom, and I was using Atom before that.
And then you should just actually be able to run it, but I'm not sure. Like there's a run menu item at the top. I don't know if it's just F5. Start debugging. Yeah, that's it. Okay, but then you have to figure out where the where it's
Yeah.
actually loading it in
Try
the,
that first
in the
one.
source code.
This one?
Yeah, might as well try it.
Claim plus plus. Okay. Yeah, that's the one.
Let's see if it does it.
It's gonna do.
Oh well, forget it then.
3 errors.
Yeah, you probably have to set it up for this project or something. Although, like, I just use Visual Studio Code as a debugger without actually having a project, but I guess I must have set it up so they didn't have to build.
You can use Visual Studio as a debugger without having a project.
Actually, is this including standard the algorithm header? If you look at the standard library includes, if you scroll down just a little bit in the source code, is algorithm in there? Yeah. Okay.
It's already there.
Yeah. Standard
it-
clamp gives a lot of headaches.
So it does seem like your printing out is probably the best solution, so we don't have to figure out how to make a debugger work.
Yeah.
Yeah. Yeah, that's quick and easy.
Yeah.
So if you want to find where it's loading, and then we can.
Or it's loading.
Right. The bin files. Yeah, if you just do a Control F for .bin.
Okay, here. It's grid number.bin. Okay.
Okay, and they're opening the file in binary mode, and then reading it in with an iterator.
We just want to see if it's reading this, right?
Yeah. Well, maybe just
We can also just do like go down like 398 or 400. I think it's worth looking at it, right? Is that right or not? Or is that that's it's where it's rendering. You kind of just want to write a for loop and go through it and find out if it's all 0 or not.
right. Yeah. So once you right after that ifs.close, we can just iterate through the flat array.
Yeah, like on 385.
Okay, do what here?
Yeah, like for size t whatever I equals 0, I less than the cubed resolution, that grid.base resolution times itself 3 times. Yeah, less than that. Just look at grid density. Well, okay, shit, that's okay. Yeah, I guess treat that as a float pointer, and and just write out the floats. Does that make sense?
Something like just copy line 398 and put it up there.
Yeah.
Right here.
And then you have to change height. So go up and where it says grid.base resolution on line 383.
Actually, you can just grab that grid.
Grab that whole thing. Yeah, or just grab the grid.base resolution thing and then put it in there instead of height.
Because we need,
Or you can use completion to put it in there.
Grid base resolution. This stuff?
Yep.
right, and just replace height with that. For the control on the for loop.
On 386.
You see what we're doing? We're basically wanting to go and touch every voxel there, so we're going to iterate through the flat array.
Okay.
Yeah, so
No.
just go to height and then press Control D. I use Sublime too. So, and then Control V, I guess, right?
Mhm.
Paste.
Oops. Push Control C. So if this.
Okay, yeah, you gotta copy
want-
that. Yeah.
you want to- okay.
Yeah.
Okay, I get it. You're trying to
Yeah.
make the
Yep.
end go here. Okay.
And then we can look at just print out for C out, whichever you want to do, and just do grid.density data.get, and then do square brackets after that, because I assume that that's a float pointer. I haven't actually looked at this code. That first argument in ifs.read on 383, if you just take that grid.density data.get and then just put square brackets after it and reference it with J. Yep. And then you'll need in the formatting string just for a float.
Was it F? I forgot what float is. No,
Yeah,
I think that's
F
right.
or G or something.
like that.
Mhm.
Okay.
Or yeah, whatever it is.
It's been a long time since I read printf.
Let's try.
So you could also, so it looks like all zeros are,
Big patch of zeros anyway.
yeah, well,
It
pipe
might
it to a
be-
file. That's what I usually do.
Yeah, that's actually a good idea. Yeah.
I was gonna do like
Okay. Yeah, now I could just go back to the editor and open that one.txt. Okay, now you can search in there, but it should be all, it's probably all zeros.
Okay. So they gave you bad data, it looks like.
okay. Well,
Or it doesn't load properly.
or maybe
Maybe-
it's not loading or something.
Maybe try opening the .bin file,
Yeah, that's something we could try. Yeah.
even if it's just in
Oh,
VS
yeah,
Code or something. You know,
I think
you
yeah,
should be able to.
Sublime is smart enough
Oh,
to
this is
do
all.
that. Yeah.
So data might not actually exist.
Well, I guess this could just be like the edge or something, though, right?
Depends on
Maybe-
how big it is. Oh, it's
Maybe
huge. Yeah.
pick a grid value in the center.
So you can actually do regular expression search in Sublime as well if you want to see if it has something that's not zero.
They're like in the middle somewhere, 44. Oh,
So
I have-
do control, go back to Sublime and then
Yeah.
do Control F. And then on the very left side, there's a little dot star.
Yeah.
Okay, and then I don't know what the regular expression is for not 000, but
I think it's the up caret and then in square brackets 0. I could be totally making that up.
I think that just means starting with 0.
yeah.
Is it? Okay.
I think if you in the square brackets, if you just type in 1, 2, 3, 4, 5, 6, 7, 8, 9.
Oh, there you go. Yeah, that worked. So
Okay,
there was
so it
some,
does
there's
have-
some stuff in there. Yeah.
mhm. Okay. So mostly it's zeros, but it's got some stuff.
And that makes sense because a lot of what they were showing had a lot of negative space there. So
So
Okay.
now you probably have to, I mean, it'd be so much easier if you had a working debugger and then you just step through the code and see when it's,
Yep.
calculating the value. But otherwise, it's going to be a lot of work to figure out where it's not, where it's breaking.
yeah.
But debugger is your friend, and
Right.
like debug breakpoints where you can actually set a expression that it only breaks if it's true.
Well, I'll work
Right.
on that then this week and then come back next week maybe.
Yep.
Cool.
Do that.
Yeah, the stuff next week, I'm not super familiar with the radiative transfer equation and volume rendering equation. I might have to read ahead a little bit on that one. Not super familiar.
Okay, cool. Well, that's fun. Thanks.
Yeah, cool. Yeah, hopefully that it's not too difficult to get working. It's looks like the data is there. It's just maybe something in the loading, maybe something in hard to say.
Oh, Omar said the problem with VS Code is that it's not C++17 by default.
Oh, that makes sense. Yeah, you gotta tell it what C++ standard to use.
Okay. I'll try that.
A lot of times it's just like dash std equals C++ 17, something like that.
Yeah.
For the compile command.
Yeah, because I needed that in the command that I ran in the DOS prompt.
Mhm.
It's in the file. They show you the dash std equals sequence of 17.
Yeah, and you can save yourself a little bit of trouble, like like on the command line where it says -o render, just change that to -o render.exe, and
Oh
then
yeah,
you don't have to rename anymore.
that's right. That's true. Cool. Yeah, so this one didn't work. The next one also didn't work, but the previous ones worked. So it's interesting.
So I imagine that's probably something to do with the data loading then. If the rest of the code is pretty much the same.
Mm. Yeah, because the dot / convention on Windows might have some issues.
Oh yeah, I had to give it. Yeah, that's the thing is I tried to port some of my code that I run on Linux to Windows, and I had to give it absolute paths. I had to give it from the drive letter to the file. It was like Jesus Christ.
Let me try to remove the dot /. See what
You shouldn't need to do the whole path, but yeah, the dot / might be messing it up.
Yeah.
Let me try. Let me see if just remove the. Okay, let me try this again. If it's that simple, that would be nice. But rarely do we get this lucky. Oh, let's see. Do we have?
I'm gonna cut off the recording here.
Yeah, nothing.